So yeah, so that is the big reveal. Doing the work from home thing. People have gotten a lot more serious about the working from home thing, and hence even I'm working from home now because I can't get in anywhere. So yeah. So I've been testing out some stuff. I bought like this tablet thing that I'm gonna write on, and like I hope the technology doesn't freak out on me. But yeah, we're doing big things, we're doing new things, and we are going to hope it all works out. Yeah, I'm turning into Khan Academy, exactly. Except I'm not gonna have as cool a background maybe, and I probably won't use as many colors. Jhevon Academy. Okay, so since I don't really know how to write very well on this thing yet, my idea was to use OneNote, in which some things I'd alternate between typing and actually writing. And I think that might work out better. So no word on upcoming exams yet. Still waiting. I am just as eager to find out about that as you are, actually. Okay, so I assume everyone can see the whiteboard. Okay, well, it's not really a whiteboard, it's OneNote. All right, so to get things a little bit more streamlined, I pre-typed some stuff, which we will be going through. And oh, I have actually thought of ordering a whiteboard. I was gonna order a chalkboard. I was very tempted, but I figured that's gonna create too much of a mess. So yeah, I am looking into ordering a whiteboard. The thing is, a lot of places also, their delivery times are longer because they're prioritizing shipping things that can help with the pandemic. So even like Amazon now, they give you like a month. So it's finding a whiteboard is one thing. Finding somewhere who would ship it immediately is a whole other thing. So yeah. But anyway, let's actually begin. Let's get into this. So here I am, first line. Last time we spoke about convergence of Taylor series, which is a very, 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 very muy importante thing. A key takeaway from that discussion was, let's see if I can get this drawing tool here to work out. Okay, so a key takeaway from that discussion was that if our remainder term approach 0 as n, this is harder than I thought, approaches infinity, then it turns out that your Taylor series, oh, I don't know what that, it turns out that, I don't know why it's doing that, turns out that your Taylor series, n goes from 0 to infinity of f to the nth derivative evaluated at x naught over n factorial times x minus x naught to the n will approach the original function that generated the series in the first place. And that was important because now what that means is we can think of the function f as being equal in the strictest sense to its Taylor series. So it's Taylor series. Let's just write out Taylor series. That's easier. And one thing I wanted to emphasize here as well is this equality, as long as you're in the radius of convergence of the series, the equality, it really means being equal in every sense of the word, meaning if I plug in a value into f of x, it's the same as plugging in a value to the Taylor series. Anything I do to f of x, it's the same as me doing that thing to the Taylor series. The graph of f of x is the graph of the Taylor series, etc. And yeah, that just goes with everything. Now we have done some things where we did math with series, but I wanted to show you something cool. So now we're over here. A point that I emphasized before, is that when it converges to a function, anything that's done to the function, you can do to the series. And we've done some things. I just actually wanted to show you a derivative example here. You could actually talk about now rederiving all the formulas that you know about if you know the corresponding Taylor series for the functions. Pretty much all the formulas that we know about, you can rederive them using series. So for example, if I wanted to find the derivative of sine of x, now we all know the answer is cosine of x, but is it actually the same as taking the derivative of the Maclaurin series for sine of x, which is x to the 2n plus 1 over 2n plus 1 factorial? Now, we know that if you are absolutely convergent, which we know this is the same as just taking the series of the derivative. And here, this is 1 over n. Notice that 2n factorial is actually 2n plus 1 times 2n factorial. And if I differentiate the x part, you bring the power down, 2n plus 1, and you subtract 1 from the power. So that leaves it with 2n. Then what happens is, this is taking way too long. Then what happens is this, you can cancel. Oh, okay. Okay. You can cancel that. And what you'd realize is going to happen now is, where's that pointer? Okay, boom. This is going to be the series n goes from 0 to infinity of minus 1 to the n, x to the 2n over 2n factorial. And if you have all your Maclaurin series memorized, you'll realize that that was actually cosine, right? Meaning, so every formula that you know, if you know the corresponding Taylor series for the functions involved in those formulas, you can actually go through and prove series versions of all these formulas. And it's really cool. And some people are asking me about the Taylor series for tangent. You could actually do that. You could actually take the series of sine, divide by the series of cosine, and get tangent. Although a nicer way to do it would probably be to realize that tangent x times cosine x equals sine x, and create a generic series for tangent x, multiply out the terms, and then match up the coefficients on both sides of the equations. You could figure out tangent x that way as well. So, and you also, for the Taylor series for tangent x, you could use straight up the Taylor formula. F to the nth derivative evaluated at the point over n factorial times x minus x naught to the n. That formula, doing it that way though, it's really hard to find a general formula. You can do it in terms of Bernoulli numbers, but that's way beyond our pay grade. And yes, this only applies if the series converges. If the Taylor series diverges, it doesn't make any sense. And this part, the Rn approaching 0, also says it's convergent. So yeah, once it's convergent, anything you can do with a function, you can do with the series. And that's pretty neat because this allows us to figure out a lot of things about functions in an easier way, sometimes easier way. We saw this with integration than it would be without series, as well as it gives you another piece of insight into these functions. So for example, we know that the sine of x function is an odd function in terms of symmetry. And we know that the cosine of x function is an even function in terms of symmetry. And it turns out the power series for sine only has odd powers, and the power series for cosine only has even powers. That's not a coincidence, right? So all odd functions and even functions behave that way. Their power series correspond accordingly. And that's one way you can actually know that the tangent function is an odd function. If you actually derive its power series, you'll notice that only the odd powers are present. And yeah, which is interesting. So yeah, that's something I really want to hit home. Once you have a convergent Taylor series and it converges to the function that generated it, you can treat them as one and the same. And that's something that's super important. Of course, we will see applications of that in this class, but very few applications. In future classes, that's where you're really going to realize that this comes in handy a lot, especially in a class like complex analysis, which is also used all over the place in engineering and science and a lot of applications. A lot of things we know about complex analysis, we figured it out using series. In fact, we use something called a Laurent series, which means it doesn't start from 0. It actually starts from -infinity. Like you have this the polynomial going counting powers in both directions. And using series like that, we could figure out a lot of things about complex numbers and how functions work in the complex plane. So series, very applicable. Once a Taylor series converges to a function that generates it, they are one and the same. So you can figure out things about the function by using the series. You can figure out things about the series by using the function, etc. One very, very important application for us, scrolling down here, is an example like example 1 that we have here. So that is similar to an example that we did in class last time, and it's actually a very important kind of example to know how to do, because straight up problems on a final or a test, if whatever that's going to look like, this could be its own problem on a final or a test. It's definitely something that I would ask, and something that it's like there's over a 90% chance that if you're taking a departmental final, a problem like this will show up, where they're going to actually ask you to use a series to help them evaluate an integral. This is the example 2. That's a little bit more into optional territory, and I'll talk a little bit more about optional things as well. But I think they're really cool, and I think in the future you are going to make use of all these things. So I'm going to talk about them anyway and spend a little bit of time on them. But example 1 is definitely, this is very important. So I don't know, maybe I can bold that. Example 1, super important. It's definitely a problem type that you need to know how to do. And we actually saw a problem like that before. So let's actually work that out. Example 1 solution. All right, so maybe someone can chime in here and tell me how to do this one. It'll be a good review or prep. Anyone? Oh, let me scroll up so you can see the example. Find a Maclaurin series for e to the minus x squared. Okay, compare it with the Maclaurin series for e to the x. All right, what is the Maclaurin series for e to the x? We know, or we should know, that e to the x can be written as a Maclaurin series. Doing a little bit of lag here. What is it? Are you shouting at me, Jesse? No, that's a factorial. X to the n over n factorial, right? Jesse's like, x to the n over n. No, it's n factorial. So that is the Maclaurin series for e to the x. That's something that you should know by heart. And like I said, we know that that guy converges to e to the x, which means anything I can do to the e to the x, I can do to that power series, which means, where's my pointer here? Which means I can think of e to the minus x squared as just actually plugging in x squared for x in this guy. So I can have x squared in here. Right? And so that is going to be the series of x to the 2n over n factorial. And that's our Oh, there is no minus sign for e to the x. Oh, you mean minus sign here? Yes. I thought you meant in the original form. That should be a minus sign. Ugh. Don't know what's happening. That should be a minus sign, and which means there's going to be a -1 to the n. Yeah, that's a good save. Okay, so this means I can think of the e to the minus x squared as that guy. So that's your answer right there. Yeah, right now I'm playing around too much. Where's my pointer? Yeah, I don't think that's me. I think that's the computer is kind of freezing up and whatever. We won't do it. That's the answer though. That is the Maclaurin series. So that is the answer to part A. So part A, and that's our answer. Okay, so now part B. Using your answer above, estimate that using a sum of two fractions. So what are we going to do? Right, so so the first thing is you're going to realize is that the integral from 0 to 1 of e to the minus x squared dx, we can think of that as the integral from 0 to 1 of the series -1 to the n x to the 2n over n factorial. This is from n goes from 0 to infinity dx. And because of absolute convergence, we can actually switch these two. And do that. And that brings us to right. And now this -1 to the n over n factorial, that's a constant. So I'm just going to leave that alone, -1 to the n over n factorial. And I'm going to integrate the x part. So it's x to the 2n plus 1, add 1 to the power, divide by the new power, 2n plus 1. And of course, we plug in 0 and 1 here. And so let's move this guy out the way. And move this guy with it. That's what we're going to talk about after this example. And so where we are is if you plug in 1, of course, if you plug in 0, everybody's 0. So if you plug in 1, you would have n goes from 0 to infinity of -1 to the n over n factorial times 2n plus 1. Now, we know what that is. That is so this is going to be plug in n equals 0, you would get 1 over 1. Plug in n equals 1, that's -1 over 3. Plug in n equals 2, you would get +1 over 10 minus ... right? So that keeps going. And what we can see here is that, well, the answer is just for us to approximate and use the sum of two fractions. So I would approximate that by that guy. So our approximation is, it's approximately 2/3, but it just says use the sum. You don't have to simplify it. Yeah. So 1 minus 1/3 would be my guess for what this definite integral is. And I did that using series. Now, of course, you can appreciate, hopefully you can appreciate the power of what we just did, because e to the minus x squared has no general antiderivative. We do not know how to write the antiderivative for that, that function. And this is the answer in series. And basically what that means when we say that is that this is actually the answer to the integral. And by the way, this series here would represent the indefinite integral. The thing is, that series doesn't converge to any function that we're familiar with. So that is the idea here. Once you can write it as a familiar function and not as an infinite sum, we say that you've written it in closed form. And we say that you've written it in closed form. Hold on, I'm just checking something else here. Okay, we say that you've written it in closed form if you can write it as a nice little function that's not an infinite sum. But other than that, the series would be your answer. So in here, we're approximated with 2 fractions. Now, part C, give an upper bound for the error in your estimate above. So how would we do that, part C? Alternate series approximation theorem. All right, so where are we here? So part C, by the alternating series approximation theorem, the third term provides the upper bound. Which is why I wrote out the third term, even though technically we didn't need it for the answer. So this means the magnitude of our error, that should be absolute values, is going to be less than or equal to 1/10. Right? And I can, well, let me see something here just to show you guys. Yeah, so that's roughly the actual answer to 6 decimal places. I can get from Wolfram Alpha. You can actually type that in, and it's 0.7 something, right? And 2/3 is 0.67, right? So we are within 1/10 of the actual answer, which is pretty cool. Yeah. And of course, you can just keep going until you have a nice estimate that you want. So for example, because Wolfram Alpha gave me 6 decimal places with the answer, it means that Wolfram Alpha just kept going until the next term was less than 0.000001. But yeah, that leaves this example here. The Maclaurin series for e to the x you should know by heart, but that automatically means anything I plug into e to the x, I can just plug that thing into the series. And that can give me a Maclaurin series for this guy. And Then I can do integrals with it, I can do derivatives with it, I can do whatever I want with it, but the particular example was about doing a definite integral, because the derivative is easy. We can do the derivative here, no problem. And then we can actually judge how close we are using one of the estimation theorems that we have, which, as I mentioned before, more than likely in a class like this, the alternating series approximation theorem is what you're going to be asked about, because it's the easiest one. The next term tells you how close you are to the actual answer. So a problem like this, which we did an example like this last time, is definitely one of the kinds of problems that you need to know how to do. Any questions on that? I guess not. And you guys are able to unmute yourselves, correct?
Yeah.
Okay, all right, good. Okay, so hopefully that wasn't so bad. Very standard type of problem. So, and it all comes down to you having memorized some sort of power series, right? So I can ask you any problem where knowing what the series for 1 over 1 minus x is, or e to the x, or sine of x, or cosine of x, any of those I can ask you a problem like that, and you should be able to use the Maclaurin series to figure it out. So that's very, very muy importante. Let's talk about another application of Taylor series. So there is this equation. It's called Euler's equation. And it's this guy right here, right? Very important equation, very, very useful. And it leads to one of the most beautiful equations in mathematics, as some people call it. And what we're going to do in the next example, I wanted us to actually prove this. It turns out you can prove this without too much trouble by knowing about series. So did anyone actually do that? Ideas for how to go about getting this proven as a series? Well, using series. Oh yeah, Euler's identity is the equation I'm talking about. Which, let's see if I can find that. Maybe later. Let's not risk it. I was gonna look up the video for what I'm doing. Yeah, you wouldn't. I probably wouldn't plug in on both sides because then you wouldn't be able to move anything. You'd have to keep both sides separate and kind of show that they simplify to the same thing. But yeah, so one thing you'd probably need to notice here is what I is and how it behaves. So remember, I was the square root of -1, which I told you guys. Of course, that means that if I were to take I squared, what would I get? -1. And so then my I cubed is going to be minus I, because I just multiply I squared by I. My I to the 4th would be, well, now it's minus I squared, so that would become +1. And then you take your I to the 5th, you would get I, and you'll notice that that means the process is going to repeat once I start finding higher powers, right? So I, upon repeated multiplication, it starts repeating its value after four multiplications, right? So it starts out I, I squared is -1, I cubed is I to the fourth is +1, then it goes back to I, and then the process repeats. So that will help you figure out some patterns later. So now you can start off with, I don't know why it does that. You can start off with E. Oh, I think something else is touching it over here, confusing this board. It's very sensitive. Okay, where are we? You can start off with E to the I theta. That is just going to be the series. That is going to be the series. N goes from 0 to infinity of pretty much I theta to the N over N factorial. And now you start to write out what that would actually look like. When your N is 0, you just get 1 plus, when your N is 1, you would get I theta plus, when your N is 2, you get I squared theta squared over 2 factorial. When your N is 3, you get I cubed theta cubed over 3 factorial. When your I is 4, when your N is 4, you get I to the 4th theta to the 4th over 4 factorial. Let's write out a couple more. Plus I to the 5th theta to the 5th over 5 factorial, plus I to the 6th theta to the 6th over 6 factorial, plus dot dot dot. And then what you can do is you can actually just replace all your i's with what you know they are based on the above line. So where are we here? So this is just 1 plus I theta. The I squared is -1, so that's minus theta squared over 2 factorial. I cubed is minus I. It's minus I theta cubed over 3 factorial. I to the 4th is +1, so that's plus theta to the 4th over 4 factorial. I to the 5th is I, so that's plus I theta to the 5th over 5 factorial. Then that's going to be minus theta to the 6th over 6 factorial, etc. Dot, dot, dot. And what you can do here is you can group all the guys without the i's, and then group all the guys with the i's. And so without the i's, I have 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial plus dot, dot, dot. And then the guys that are attached to the i's, I have theta. And then I have minus theta cubed over 3 factorial. Then I have plus theta to the 5th over 5 factorial. Then I would have had a minus theta to the 7th over 7 factorial plus dot, dot, dot. And at this point, you're like, I actually know that series. This guy here is actually the Maclaurin. Let's go very slowly. This guy here is actually the Maclaurin series for cosine theta. And this guy here is actually the Maclaurin series for sine theta. And so you just get this guy is equal to cosine theta plus I sine theta, which is cool. You get this nice little identity here, which I don't know if I'll get back to this. Maybe I'll come back to this, but we're going to do something called polar coordinates later, where we're going to kind of think of the XY plane in terms of sines and cosines. And you're going to realize that there's going to come a point, probably not in this class, where we're going to be able to think of sines and combinations of sines and cosines as exponentials. And we actually use that to derive a lot of things as well. That's actually super convenient. So yeah, e to the I theta is equal to cosine theta plus I sine theta. And there are several proofs of this, but this is one of the main ones. It's one of the nicest ones, probably the most intuitive ones, once you actually are convinced of the series and the function being the same thing. So that's pretty cool. Now, what you can do after that now, if we plug in theta equals pi, so I'm thinking of theta as some angle, this gives you that e to the I pi is equal to cosine of pi plus I times sine of pi. And we know that cosine of pi, or we should know, is -1. We know that the sine of pi is 0. And so pretty much you get that e to the I pi is equal to -1. You're going to use that in differential equations for sure. It'll apply it to in other places as well. And then you just add 1 to both sides. E to the I pi plus 1 equals 0. This, ladies and gentlemen, and this is totally ruining how grand a moment this should be. But this, ladies and gentlemen, is called Euler's identity, which to fully understand why math people geek out about this so much, you probably have to take a class like abstract algebra, where you pretty much reconstruct the real numbers and you construct math from an algebraic standpoint in terms of symmetries and patterns and all that kind of stuff. And so you start to look at sets like the real numbers in terms of additive identities, multiplicative identities, and operations that work on the set. So the main operations are addition, multiplication, and exponentiation. You kind of think of subtraction as a kind of addition, you kind of think of division as a kind of multiplication, and you kind of think of radicals as a kind of exponentiation, by the way. And so what you have in this very short equation is you have exponentiation here in the power. E is raised to the I theta. You have an addition here being adding to the 1. You have 0, which is the additive identity of the real numbers. You have 1, which is the multiplicative identity of the real numbers. You have the addition operation, the multiplication operation in the power. You have the exponential operation. You have the equality sign. So pretty much every important mathematical operation is in this equation. Also, on top of that, all the important mathematical constants, E, I, and pi, are in this equation. 1 and 0, of course, very important mathematical constants are in this equation. And it's really awesome that all these guys, all these important guys, the most important operations in mathematics and the most important constants in mathematics kind of collude with each other to come up with this equation. And you can get to this equation by using series, which is very cool. So I should probably have a guy talk about, so I'll probably YouTube, I think the guy Koshen Lo. This professor from Carnegie Mellon, he actually geeks out about it, and he's like very excited. He's going to be a lot more excited than I am because he's not writing on one of these things. But you can look that up, and oh, that's the video you saw. Yeah, right. It's like he's so excited when he's talking about it. he's happy as doing math. He was meant to be a mathematician. But yeah, you can look up that video, and there are many other videos that you can look up about this thing. It's really a big thing. And if you were to Google the most beautiful equation in all of mathematics, most websites you go to would list this as #1. It's a big deal. It's called Euler's identity, and now you know how to even prove it. Now you know what it is, and we're probably not going to see it in this class unless maybe it's some sort of bonus problem, but you'll definitely see it as early as 391, which is differential equations. Very important equation, super useful. It's super useful in complex analysis as well. It's just an all-around neat equation. And the useful one I'm talking about is this very useful equation. This is just beautiful, right? It's you use it, but it's more there for its beauty. Or we like it because of its good looks. Okay, so that is another application of series. to derive one of the most important equations that you can come up with that leads to one of the most beautiful identities that you could come up with, called Euler's identity, of course, named after the mathematician named Euler. Pretty cool stuff. Another application I wanted to talk about, which will go here, is a generalization of the binomial theorem. Now, the binomial theorem is this guy over here, which is a guy that tells you how to expand a binomial. So a sum of two terms is called a binomial, right? And when you raise it to an nth power, raise it to a power, you want to know how to expand that. And so it turns out you can actually write this down as a series. So let me actually just write something down. So for example, let's say I wanted to know how to actually expand x plus y cubed. I can actually follow this series formula. That is going to be 3, choose 0, x to the 3, y to the 0, plus 3, choose 1, x squared, y, plus 3, choose 2, x, y squared, plus 3, choose 3, x to the 0, y cubed. Now, this guy over here, n choose k. Now that is something that's called a combination, and you'll see that in math classes like probability and statistics. Right, so that's what I'm talking about. This guy here, I'm answering that question now. This is called n choose k. It's a number that you talk about in probability and statistics. It helps you count certain things, meaning it's actually the number of ways to choose k objects from n objects in no particular order. And we counted that it's actually n factorial divided by k factorial over n minus k factorial, which you can write that in another way, which is, this will be useful for what I want us to do later. Make some space here. Another way to think of that, because you can flesh this out a little bit and cancel the n minus k factorial. So this is going to be, let me move the chat box out of here. You can write this as n times n minus 1 times n minus 2 ... going all the way down to n minus k plus 1, because the n minus k factorial is going to cancel this guy, and divide all of that by k factorial. So for example, if I say, what is 10 choose 3? I can think of that as basically 10 factorial over 3 factorial times 7 factorial, which I can think of that as 10 times 9 times 8 over 3 times 2 times 1. And then the 3 would cancel into the 9, 3 times, 2 would cancel into the 8, 4 times, 3 4 is 12. So this is 120. And what that is the number of ways that you can pick 3 objects at random out of a group of 10 objects. So if I have 10 people and I want to create a committee from those people of 3 people, no order, there's no title, there's no first or second person. I just randomly pick 3 people from that group of 10 people over there. How many ways could you possibly do that? 120 ways. There are 120 different possibilities of groups of 3 people that you could create, right? So it's given by that guy. It's given by 10 choose 3. That's why it's called 10 choose 3, right? So when you're picking some objects from another set of objects without order, it's said that you're doing a combination, and we can calculate how many ways you can do a combination by using this number n choose k. So by the way, if we take that here, if we take this understanding here, what this basically means, 3 choose 0 is actually going to be 1 if you follow that definition. So you only have x cubed. 3 choose 1 is going to be 3. Turns out that 3 choose 2 is also going to be 3. And then your 3 choose 3 is actually going to be 1. So if you have a group of 3 people, how many ways can you choose 3 people? Well, one way. You have to choose everybody, right? And that's it. If you were to expand, multiply out x plus y all cubed, that's what you would get. X cubed plus 3xy plus 3xy squared plus y cubed, right? So the guy, and you can do this for higher powers. So normally we think of our n as a positive integer, and it tells you how to do this. Another way to look, now this is for you algebra buffs here. Another way is to use something called Pascal's triangle. So you start with a triangle of 1, then you have 1, you add these 2 guys over here, you get 2, then you end with 1, 1, add 2 guys between them, get 3, 1, add those guys, you get 4, add those guys, you get 6, add those guys, you get 4, 1, etc. You'll notice here, there is a line that says, let's try highlighting. There's that line here also is the same as the coefficients here. Right? 1, 3, 3, 1. As you can see from this line here, if I wanted to expand x to the 4th, x plus y all to the 4th, x plus y to the 4th, I would just use these as the coefficients, right? It'll be 1, 4, 6, 4, 1. You start with the highest power on the x to the 4th, then you count down, x cubed, x squared, x, and then x to the 0. Then you start counting up with the powers of y to the 0, y to the 1, y squared, y cubed, y4. Then you add them. Right? So that's another way to do it, right? So there was a problem on the final exam for Calc 1 last semester where they asked you to use the definition of the derivative to derive x cubed, where you needed to expand x cubed. And I just wrote this formula down on the board because I figured a lot of people wouldn't remember this from algebra class. But yeah, I just did it really quickly in the top of, it wasn't huge. It wasn't bad if you knew this, right? But I knew my students wouldn't know it, probably, most of them. So I just wrote it down on the board and I did it really quickly. And I didn't have to multiply it out. I just knew Pascal's triangle. Oh, it's 1, 3, 3, 1. And I just wrote it out on the board and gave it to them. But now you know, it's going to come in handy every now and then. Now, it turns out that these guys here, it turns out that the combination is connected to Pascal's triangle. Meaning these guys here, if you actually calculate them, you'll realize that this is actually 4 choose 0. This guy would be 4 choose 1. This guy is 4 choose 2. This guy is 4 choose 3. And this guy is 4 choose 4, right? The coefficients are always going to line up with Pascal's triangle, right? So, and that's basically what the binomial theorem says. It's this guy right here says exactly that. Here's how you find the coefficients to multiply out a binomial, okay? Now, usually, n is considered a positive integer. But we're going to generalize. We'll generalize this. How are we going to generalize? Well, we're going to use Taylor series. So it turns out that if we find the Taylor series of x plus y to the n, where you can think of your y as a constant if you want, and just think of your x as the variable. It turns out that this guy actually gives you an infinite series. It will be the series, it will look like the series n goes from 0 to infinity. Touching something here. Where are we now? Okay, so this guy would look like this series. N goes from, or let's put k. Let's put k. Where are we? Okay, so it'll look like k goes from 0 to infinity of n choose k, x to the n minus k, y to the k. And it'll actually become an infinite series. Now, how we usually reconcile this with the binomial theorem is that we just normally think of this guy as being undefined if your n is anything other than a positive integer. And if we relax that requirement and we allow our n to essentially be anything, we can actually apply this formula up here, this guy up here. If we just take that to be the formula where n can literally be anything, and plug it in here, we can actually figure out how to expand things that are not where n is not a positive integer. So, for example, so here's an example. That's another, these are some other applications that I'm going to talk about later, but we'll move them down here. Okay, so here's an example, just to see where we're going here, because there's a punchline I want to get to. Okay, so this means, for example, by using Taylor series, using Taylor, if I had something like 1 plus x raised to the n, this is actually going to look like a series. K goes from 0 to infinity of n choose k, x to the k, right? So that is going to look like n choose 0, which is always going to be 1, by the way. Then you're going to have n choose 1 times x plus n choose 2, n choose 2 times x squared plus dot, dot, dot. And now if we just relax what the n can be, you're going to see something cool. So what if I wanted to do something like the radical of 1 plus x? I can think of this as 1 plus x to the 1/2. Then I start to expand this as a series. So my n is a half here. So this is a half choose 0 plus a half choose 1 x plus a half choose 2 x squared plus a half choose 3 x cubed plus dot, dot, dot. And so now you might be saying, well, how can you choose one thing from a half a thing? That's why it doesn't make sense in a probability standpoint. But if I use this definition down here, then this would actually become 1 plus, take this as a half times a half minus 1 over 1 factorial, plus take this as a half times a half minus 1, which is minus a half, times that minus 1, which is minus 3 over 2 factorial. This is, oh, I'm actually jumping the gun here. This is actually the second factorial one. I'm jumping the gun. Following the form that I wrote up top. Erase, erase, erase. Delete, delete. That's a Death Note joke there for anyone paying attention. Okay, so this a half choose 1 is actually just a half. N choose 1 is always n by that formula. So that's x plus. Now for 2, yes, for 2 the denominator is 2 factorial. On top of it, once you have a factorial, you just have 2 factors on top, right? So for the 1 factorial, you had 1 factor on top. That's x squared. Plus, for the guy with 3 factorial, you need 3 factors on top where you just subtract 1 counting down. So it's a half, then a half minus 1, then a half minus, then minus a half minus 1, x cubed. Plus the next guy is going to look like, the denominator is 4 factorial, so you need 4 factors on top. So it's a half minus 1, that minus 1, that minus 1, x to the 4th plus, and you continue. And then you're going to have, we can simplify this. So this is 1 plus x over 2 minus, this becomes x squared over 8. Minus and minus is plus, the 3 is going to cancel into that 3, and I'll get 16. Plus x cubed over 16 minus dot, 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 right? So I can actually expand the radical. Now, note what this means. If I had the radical of 1 plus x squared, that would actually expand as 1 plus x squared over 2. My 1 plus x over 2 yeah, same substitution logic. Plus, oh, so yeah, I was right, x squared over 2. I'm plugging in x squared here, so that's x to the 4th over 8. Plug in x squared here, that will be plus x to the 6th over 16 minus dot, dot, dot. Now, of course, what do you think students normally do when they see something like, so you have some kid sees this on a math exam. What do they like to do? They like to distribute the radical across the sum, which now we all know that's very illegal, and Jhevon's going to kill you if you do that, right? So they would normally write it as 1 plus x. Now, I want you to appreciate that they're infinitely wrong when they write that down, because you should have an infinite number of terms in the expansion of this thing. Second of all, it would have been better had they approximated it with 1 plus, if they only want 2 terms, that is actually a better approximation for the radical of 1 plus x squared than 1 plus x is. And if you actually look at the graph, that will actually make a lot of sense to you, because the radical of 1 plus x squared curves, right? there's no way that a linear function is going to be a nice approximation to that. But if you're close to 0, this quadratic actually behaves a lot like that radical. And things like that is also very useful in mathematics. Sometimes you have a function that's just very hard to deal with, like a radical of a sum. What you can do is you can look at it as a polynomial, an infinite polynomial, right? And if you have to approximate it, you can approximate it with a finite degree polynomial. So you might want to approximate the radical of 1 plus x squared with 4 terms. Then that would be the first 4 terms. And it's a much better approximation than the incorrect idea of just expanding the radical would be. That's very wrong. Okay, so yeah, I just thought I would show you that because that's a very common algebra mistake, and I want you guys to realize just how wrong it is. If you are going to expand a radical, you need an infinite number of terms. And this was something I mentioned to my Calc 1 class, but now in Calc 2, I guess now I get to show you guys how it would actually work. Is this very important in the sense that for this class, like, would I actually ask you to repeat something like this? No, this is this is fun. Okay. But yeah, I just thought I'd show you. Here's how you'd expand a radical. And you can even think of this as how you'd expand a cube root or a 4th root or a 5th root or something like that. You can go through this sort of idea. It's kind of getting dark. But yeah, here is, so that's an application of Taylor series. Another one, here is another one. Just want to give you guys some ideas of how useful these guys are. Another application. So one application is just generalizing the binomial theorem. This allows us to expand all sorts of crazy things and all sorts of crazy powers. Just by realizing the Taylor series for the binomial expansion, it looks exactly like the binomial expansion, except it goes up to infinity as opposed to stopping at a number, where the original formula stopped at a number. Another application is something like limits. So for example, you have this limit here. Limit as x approaches 0 of sine x minus x over all over x cubed. One way you could do that is using L'Hopital's rule. Of course, you'd have to apply L'Hopital's rule 3 times. There are a lot of examples. My watch is reminding me to get up and take a walk. Like, everyone get up and stretch. Yes, I am wearing pants, which is, if there was ever a benefit to working from home, it's that you wouldn't have to put on pants. But yeah, as a courtesy to y'all, I am actually wearing pants at home. The things I do for you guys need to appreciate. Okay, so let's say I have this limit. Now, of course, one way is L'Hopital's rule. Another way is we can actually, oh, I still have the red pen on. That's way too aggressive. Let's actually just change the color here. Another way to look at this, we can use series. Okay, so for example, if I have the limit as x approaches 0 of sine x minus x all over x cubed, what you notice I can do is I know a Maclaurin series for sine. I can use that at any point because it's Maclaurin series. So sine of x, we know that is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot, dot, dot. Then I have that minus x off to the separate there. And then here I have x cubed. Now, notice what's going to happen. The x's cancel. This kills that guy. And I just have this infinite series over the x cubed. Now, at first, you might think, well, that's worse. That's actually going to be crazy. Like, I have to evaluate an infinite series to figure out this limit now. And the answer is, of course, no, because this would simplify. You can take x cubed and just divide into each of these. You'll get -1/3 factorial plus x squared over 5 factorial minus, the next one would be x to the 7th. So x to the 4th over 7 factorial plus ... But now you're actually plugging in zeros for all these x's. So this goes to 0, that goes to 0, and your answer is just -1/3 factorial, which is -1/6. And ladies and gentlemen, that's the answer. Now, no, it doesn't mean you get 5 minutes break. That's the answer. And you can do L'Hopital's rule 3 times and you would figure out eventually that that's the answer. But if you're really good with series, it will actually be a lot quicker to do this way. You'll just see that, oh, the sign starts out with an x and then I subtract an x. So just look at the remaining things, divide x cubed into it, and you can plug in x equals 0, and Bob's your uncle. You have the answer. -1/6 is the limit. So you can actually use series and limits. Like I said, wherever you can talk about a function, you can apply its Maclaurin series. If provided the series, the Taylor series converges to the function, you can swap in a series for a function at any given time, and it might make things nicer. What I'd like you guys to do is actually to try these. So you can take a screenshot of those. Try these using the same method. Try to conveniently apply a series, do those problems, like take a picture or something. Just getting a little dark. Yeah, so you can try those using series. And some of these you'll realize they'll be very annoying to even do with L'Hopital's rule. You have things like you have to do the product rule here and simplify, and then product rule again and simplify. Yeah, try these using series. They're actually not so bad. But yeah, that's another application I wanted to show you guys. Rushing through a few applications here because most of them, as I mentioned, aren't important, in the sense that it's not something I'm going to directly test you on unless it's kind of bonus material or something like that. The department final probably won't test you on a lot of these, but they're the kind of thing where you'll go to a future class where you use it and the basics would not be explained to you. Like they're gonna just expect you to know it. It's kind of like how in all the calculus classes, we don't do complex numbers. We don't talk about them at all. You go into a class like 391 and suddenly they expect you to know about complex numbers, right? So they're gonna just throw up this e to the I theta idea and they're gonna be like, you guys know about this, right? All right, cool, boom, 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 boom. And then they do all these things with complex numbers and you've never actually learned it. Your engineering classes are gonna be the same way. They're gonna expect you to know all these kinds of things for those of you who are in engineering, where you never really talk about them in class. So I'm talking about some of these because one, they're kind of fun and interesting and cool, but also everything I'm talking about now, there's going to come a point where it's going to be expected that you know it without warning. So I decided to kind of warn you guys about it. But the most important application is definitely being able to evaluate definite integrals, using series, because that's something that you're going to be directly tested on. Euler's equation, like I said, highly applicable, very useful in many other spheres in all your engineering. A lot of your engineering classes are going to use it. And if you're a math major, you're definitely going to use it in differential equations. You're going to use it in complex analysis. You're going to use it all over the place as well. It's kind of going to be a thing that they kind of would expect you to know about before even talking about it. And yeah, binomial theorem. Like I said, they put this on the Calc 1 final. Some of you probably remember that. This was something that they just expected you to know. No one expected you to sit there and write out x plus y times x plus y times x plus y, multiply out all the terms and group them together. They kind of expected you to know this off the top of your head. And like I said, without warning, I don't think there was never a point in the syllabus where they said we should cover this. And so that's why I just wrote it down on the board for my class, because it's like, yeah, they're not going to remember how to do that. And I don't want them to waste time multiplying out and then end up getting a simple problem wrong because they multiplied out and added something correctly. So I just gave them the answer to that. But yeah, so while strictly speaking, all these applications after integration that I mentioned aren't necessary for you to know, it'll be good for you to know them, because at a moment's notice, out of nowhere, you're going to be expected to know about these things. And no one's going to tell you that you're expected to know about them. Yeah, so limits using series is a thing. Try these examples and see if you can get the answer. And you can probably even try this using L'Hopital's rule. Try these using L'Hopital's rule as well. See how you like the difference. If you get very used to series, you'll oftentimes like the series way of doing it better. Here's another example, which for those of you who are mostly in applied spheres aren't going to appreciate this, but the math people would appreciate this. Every now and then, you'd like to write a number as an infinite sum for whatever reason, right? So you often have like these, sometimes you'll hear these math geeks, well, you can represent pi as this infinite sum, and therefore, blah, blah, blah. And they'll write out this infinite thing, and like, why do you know that, dude? Where did that even come from? Chances are it came from a Taylor series. So I'm just going to show you guys some ways of writing down things as infinite sum. We'll get some useful practice in this example as well. But then I'll also talk about, well, I won't talk about it. In something like number theory or some other highly specialized mathematical field, this often comes in handy. So if we look at, for example, write E as an infinite sum. Let's go down. After this application, I'm done with applications. So for example, if you wanted to express the number E as an infinite sum, did not mean to do that. If you wanted to represent the answer E, the number E as an infinite sum, you know that E to the X is just the series, n goes from 0 to infinity of x to the n over n factorial, which means that E, which is E to the 1, is just this infinite sum, 1 over n factorial, n goes from 0 to infinity. Which means the number E can be expressed as 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus going on forever. That guy will actually converge to E. And a lot of people who have derived E to many decimal places, they didn't all go through the compound interest formula, which is where E originally came from, because it's really hard to actually figure out the decimal places for that number. However, if you write it as a fraction, which now you'll notice that it's a little bit bigger than 2. Here's where you notice that E is a little bit bigger than 2. It's 2.718281828, blah, blah, blah. And it stops repeating after there. But I can write E as an infinite sum. And if I wanted to compute E to a certain amount of decimal places, I just keep adding fractions until I hit the number of decimal places I want. So now you realize that this is, and this will converge to 2.71. Yeah, this will converge to 2.71828 ... which means you actually know what this adds up to, by the way. So using Taylor series, I can also figure out what some random series adds up to. That actually adds up to 0.71828, blah, blah, blah. So you can write E as an infinite sum. You can tell that it's a little bit bigger than 2. You can use this to approximate E, which is what your calculator would do. For example, you type E into your calculator, it actually thinks of it as adding a bunch of fractions to figure out what it is. And it's one of the easiest ways to actually get E as an approximation. And if you want more decimal places, you add more fractions, but you have a pattern for which you can add the fractions. There's like a pattern built into it. And this kind of thing is useful in a lot of mathematical spheres like number theory. Once you see like a pattern in an infinite sum, you can actually take advantage of that for talking about properties of that number and how it would work in some larger problem. Now, going on to example B here. Now, here's where someone can chime in. This was something I brought up before, but how would you go about finding a Maclaurin series for arctangent x? And I'm going to use this to write a number as an infinite sum. But first, this is something that I would actually ask you. So this is an important one. This is an important example here. I can give you a random function and actually find a Maclaurin series for it. So, yes, good observation, David. I do not want you to do that. So yeah, you could, you could use, well, the sum n goes from 0 to infinity of f to the nth derivative evaluated at 0 over n factorial times x to the n. But you'd realize that that's really annoying. That's going to be really annoying to actually do it that way. There's a nicer way. So this is it here, moment of truth. Let's test who's really paying attention and has a little bit of insight here. So this is an important example. How do you find a Maclaurin series for the arctangent? Now, of course, if I ask you for the first few terms, like if I said, oh, find the first 3 terms of the Maclaurin series, then yeah, using the direct definition here wouldn't be so bad. You just find the second derivative and plug in well, a trig identity, how would you turn that into a series? Yeah, that wouldn't really help. Anyone else have an idea? Okay, so just to make sure we don't run out of time here,
wait, is derivative of arctan 1 over 1 plus x squared, right? So
this is correct.
So can't you make it like a geometric series, something like that?
Okay, so
I don't know how you would proceed.
What do you want to do with the 1 over 1 plus x squared?
Well, since that's taking the integral of that would get you arctan, so something like that. Playing around with it and then getting the series and then taking the integral of that series.
So think of this as the integral of 1 over 1 plus x squared.
Yes, yeah.
Okay, what do you want to do with that?
Then I think geometric series, you can make it 1 over 1 minus 1 minus negative x squared. Then can't you make it like the series of negative x to, yeah, and then you can manipulate that so it's negative.
Right. And that converges absolutely once you're between once your x squared is between -1 and 1. Let's not worry about that too much right now, though. Yeah, because this guy would converge absolutely because it's a geometric series. Absolute convergence tells us we can switch these two. And so we would have, this is -1 to the n, x to the 2n dx. So that is going to be the series of -1 to the n, x to the 2n plus 1 over 2n plus 1, of course, plus c. So you have this guy here. and goes from 0 to infinity, plus your constant. How are you going to find the plus c? Yeah. Joel cheated.
I guess I just got a head start. That's all.
people are there thinking, "Wow, Joel figured it out. Oh man,
No,
he's
no.
the man. He's the man." No, he went to the other class's lecture. He's like, Joel is like watching every lecture twice. He's like,
Gotta make
yeah,
sure I understand everything.
he's getting ahead of you guys. He's getting a double take on everything. You guys better watch out. Joel is going for his A. Okay, so now to figure out the plus C, remember one thing you can do is plugging in a convenient value, right? So this means that if you say were to example set x equals 0, you would have tan inverse of 0 is just going to be equal to the series of 0, because I'm plugging x equals 0 into the series, plus c. And that means that your c here is 0. So your arctan as a series is the series from n equals 0 to infinity of minus 1 to the n, x to the 2n plus 1 over 2n plus 1. Right? So now, that's arctangent as a series. So that was B part 1. Now in B part 2, scroll up, evaluate the above at x equals 1. Hence find an infinite sum representation of an important mathematical constant. Okay, so if I know that arctan of x equals this series, so drawing boxes is a challenge, obviously. If x equals 1, what does that mean? What would the left side become? Someone other than Joel. What's arctangent of 1? Tangent of 1? Anybody? Euler? 0.7? No, you're supposed to know the exact answer. No, Kevin, don't plug into your calculator. What's the arctangent of 1? It's pi over 4. Right, that's something you should know. Pi over 4. Okay, so now if you plug in 1 over there, you'd have minus 1 to the n over 2n plus 1. N goes from 0 to infinity. And so now we can represent a very important mathematical constant. Obviously, you guys should know that that's pi. It's just going to be 4 times that series. So I can write the number pi also as an infinite sum. Congratulations, you cheated yourself. Yeah. They should find like a way to put memes in Zoom now, because it's all our interaction is going to be Zoom for next few months. Like, figure out a way to get our entire lives on Zoom. Anyway, so this is 4 times, when you plug in n equals 0, you get 1, plug in n equals 1, you get minus 1/3, plug in n equals 2, you get plus 1/5, plug in n equals 3, you get minus 1/7, plug in n equals 4, you get plus 1/9, minus 1/11, etc. And so here you see this little nice pattern where the denominators are just the odd integers, and your numerator is just alternating between plus or minus 1, right? And it's little things like these, where when you see math people geeking out about pi, it's not just because like there's a pattern to the number. There's a way that it can be very nice, very aesthetic, very predictable. So even though we can never actually know what this number is in its totality, there's a lot about its predictable nature that we can talk about, and we can use it in a lot of stuff. And of course, we can approximate pi to within any number amount of decimal places we want. The TI-89 earlier probably used something like this to figure out what pi is, and just plugged it in pi, and then it divided by 4. So it just added all these guys and gave you as many decimal places as it wanted to give you. But that's just another approximation. Another way to think about pi. And that ends pretty much what I wanted to do. So that ends section 10.10. Now, technically in section 10.10, oh yeah, and the Taylor series is a lot more than I'm telling you right now. They're far more applicable. And even all of these that I told you, a lot of these applications your textbook didn't mention either. So your textbook definitely did applying it to integrals. It did Euler's equation, and it did the binomial theorem. But everything else, it was just me just going off on a tangent, telling you guys some other uses of it, right? Because they're really useful. And yeah, beyond what I can possibly tell you in this class, because you use it in many classes above this, and it's going to be useful. And a lot of things I spoke about here, like I said, there comes a point where everyone kind of just expects you to know it out of the blue by osmosis. But for this class, there's one thing you need to get from this section, the most important application for us is the evaluation and approximation of definite integrals. So if you look at the first example that started this whole thing, a problem that looks like that, where instead of e to the minus x squared, you could have some other function. A problem like that you should be able to do for sure. Everything else kind of optional. If I ever test you on it, which I don't know what that's going to look like, they'll probably show up in the bonus sections, but definitely knowing how to use a Taylor series to evaluate a definite integral is very important. Another thing that's very important is what we did down here, knowing how to find the Maclaurin series of some random function by taking advantage of the Maclaurin series of some other known function. That's something that you should know how to do. And then you can use that Maclaurin series to do all sorts of things. In terms of Euler's equation, very beautiful, very nice, very useful, very important. Chances are you're not going to be tested on it here. Binomial theorem, very useful, very important. Chances are you're not going to be tested on it here. Applying it to limits and other types of computations, very useful, probably not going to be tested on it here. But yeah, applying the series to integration, finding Maclaurin series of individual functions, these are things you must know. Knowing what a Taylor series, the general formula for it, how to actually construct one from scratch, if you ever have to do that. So pretty much if I tell you about a function where you can't connect it to any of the Maclaurin series that I told you by heart. So if I asked you something like, so if I ask you, oh, find a Maclaurin series, although with the binomial theorem that I just told you, you'd be able to do this, even though you didn't have to know. So if I told you, find a Maclaurin series for the function 1 over the square root of 1 plus x, right? If you're going to do that, there's nothing that I've told you. The series for 1 over 1 minus x is not going to help. The series for e to the x, the series for sine of x or cosine x, they will not help you here. Here you're going to go straight to the definition, f to the nth derivative, x minus x naught to the n over n factorial. That's how you do that, right? So you need to know how to do that also. Just using the definition to build up a Taylor series from scratch. You also need to know how to use known Taylor series to figure out other Taylor series, which might involve you integrating the Taylor series, differentiating the Taylor series, or just doing a direct substitution into the Taylor series. Very common. You need to know how to evaluate the definite integral of a Taylor series using using just you knowing what the Taylor series would look like, and actually being able to approximate an integral using a finite number of terms, and then be able to assess how good your approximation is. And as I mentioned, pretty much it's always going to be the alternating series approximation theorem. Once you see there's a -1 to the end there, that's how you're going to know. The very next term is going to tell you about how good the original approximation is. And yeah, so that's basically it. The next section is going to be, we're pretty much done with series for this class. I mean, you're going to see series again for sure in other classes. But this pretty much ends our discussion on series directly. The next topic we're going to get into is going to be parametric equations, I think. And I already started prepping notes for that right here, because now I think it's just going to flow a little bit quicker. Because as you can see, I'm not great at writing out stuff here. Drawing boxes, forget it. So I have to kind of now type out my notes ahead of time where I want the class to go. So I'll get working on that. So we start chapter 11 next. This ends chapter 10, the series section of this class. We're going into the next phase. So the first phase of the class was just me teaching you guys about integrals, how to integrate, integration techniques, and blah, blah, blah. Then the next phase was series. Now you know a lot about series, things that will even help you into the future, into the other classes. Next, we're going to talk about parametric equations, which is going to be very useful. Series was a lot more fun than integration. And it's actually more useful than integration, actually. So it's once you can find, the only thing is, if you can find the Taylor series of a function, then you can do every integration by series. You wouldn't even need to know any integration techniques at all. Because once you can write it as a power series, it's all power rule. Everything is power rule, right? Like I can find the integral of 1 over 1 plus x squared using the power rule. I can find the integral of sine of x using the power rule. I can find everything. It's just, it devolves everything into the power rule. Once you can hit something with a series, you know how it works. Now it's like you're dealing with an infinite polynomial. It's very, 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 very convenient, very useful. But that kind of ends. I probably not. That's just something for you guys to try for fun. Might be interesting for you to actually do it. I probably won't go over those limit examples. But you can try it. Try it a couple ways just to get used to the idea. Yeah, that ends the series discussion. Next time we're going to start with chapter 11. Next time being Monday. Right. So Monday we will start. So the phases left in the class are twofold: parametric equations and polar coordinates, which is kind of like a parametric equations. Then I'll probably talk a little bit about conic sections, even though it's not in the syllabus, because it will help us. Then we're going to do 3D stuff. We're going to move on to 3D afterwards. It felt like 30 minutes, really? Right, so class is not on the 8th. So as I mentioned to you guys, because we're having class this week, which technically we shouldn't have had class this week, we're just going to take a whole week off during the week of spring break. So the 8th, we're not having class. The 13th and the 15th, we're not having class. By the way, the 7th, oh, this reminds me, the 7th is a Wednesday schedule. So we're actually having class on Monday and Tuesday of next week. But then after that, I'm not going to see you until the second week after. Right? So our next class is Monday and Tuesday. And then I don't see you Wednesday. I don't see you the following Monday. I don't see you the following Wednesday. Then our next class is going to start on the 20th. Okay, so our next 3 classes are the 6th, the 7th, and the 20th. Yeah. But yeah, 3D stuff is coming. So Monday, we're going to get through parametric equations. I'll probably start, I don't know how far I'll get. Probably start polar coordinates, maybe finish that up on yeah. Yeah, I don't know if the final will be the only exam given, but not if I can help it. I'll definitely do something if it turns out the other way. But I have to hear from the math department about all that stuff. Anyway, we're pretty much done unless there are any final. Someone testing their writing capabilities. So yeah, we're pretty much done unless there are any parting questions. Okay, I guess that's it. So pretty much what we're going to see is you're going to see a video of your screen. Yes, stay safe. But yeah, I was recording this session, so I'll just post a recording of this session. I'll probably also find a way to get these notes to you guys, although I do highly recommend that you take notes on your own. And even if I give you the notes, recopy them because it's going to, it helps you. Helps you stay focused. It helps you retain a lot of material. So you definitely want to do your own notes as well. But I miss the Blackboard too. I'm not happy about migrating completely online myself, but what are you gonna do? What are you gonna do? But yeah, we will stop there. And no, if I post notes, I'll probably send a link in an email or something because I'm pretty sure the notes are saved in the cloud. Yeah, I don't like Blackboard. I probably won't use it. So if it's posted, I'll actually either download the PDF, post it on the class website, or just send you guys a link to the notes. Okay, that being said, have a good night, everyone. And we're going to stop recording.